watch a video, is the concept of spaces. So null space,
space,
column
space, column space.
Yeah.
Well, in the
I'm
space,
sure.
we can talk about a space or span of space, right? Space.
Yeah.
Space. It's just space, or from ordinary space, right? But this is mathematical space. It's not necessarily real space, or span, or sometimes span, right? That's related.
Sure.
And do you know this notation here? They sometimes use R square and R Q. What does that mean? Can you guess?
So it's the dimension of the real numbers of the.
Yeah, that's dimension of space. That's a dimension of space, or where the number can pick up. It could be n. Okay, it could be n. By the way, our space, the real space. What is the real space in the physical world? What is the real space? Which one?
Which is the real space?
Yeah.
I suppose if it's R3, it's where we live.
Yeah, that's basically this one. So this guy. Because also you can see this n here, you can see that it's called a span in mathematics, but also you can call the dimension. Dimension of the space is another wording. So it's very related, can you see? For example, if you are for the ant, so for this is y and x, right? And because ant cannot fly, so this ant here, so you can go everywhere. You can go everywhere and search for the food and return. Okay, go to another journey and then return, or go to another journey and accident. Okay, so this is span. Okay, this quadratic span. Okay, the span of this ant can go. What it can go? They cannot go beyond this 2D space. So this is a 2D space. Is a 2D space, right? For the ant, it's because it cannot fly. Okay, that's a 2D. Of course, they can drill the hole. That's another issue. But basically, this is kind of 2D space, and also the car. Another thing is the car. Okay, car can travel everywhere from city to the beach, whatever. But they cannot fly. Okay. So therefore, there's a constraint. Another is constraint. Okay, constraint. Constraint is where they can pick up where you can pick up these numbers. Okay. Obviously, in this case, in mathematics, what do they call this? And in mathematics, they call this R2. Can you see? So that when you see this notation, which means that it is represent a space with a certain dimension. Okay, and in which the word span can be used as a noun or verb. Okay, the span they can just mapping span or mapping everywhere. They can change the position, right? Now in physical world, I'm asking you that if you have the sun over here, you got Earth, right? You got Earth here, and we know that it will orbit this Earth will orbit the sun. You see. Now, in this case, in this particular case, although the space is three-dimensional, however, the Earth, have you heard that this is a Kepler's discovery that is an ellipse? The orbit is very close to a circle, but actually it's an ellipse. And these trajectories actually can be described by a plane. I forget that terminology. Do you know the terminology for this particular? So these have actually they are still in the plane. In the plane.
Okay. Yeah.
You agree that? I don't have to be circle. Okay. So therefore, as far as the Earth, the freedom, or another called the freedom, is not called the freedom. Degree of freedom. Okay. These are all related concepts.
Yeah, the idea of degree of freedom I've always wondered about because it's used a lot in statistics.
Yeah, degree of freedom. Yeah. So these are the similar ideas or concepts when we study the space in math. So space in math is similar but not identical to the space in the physical world. Yes. So that is why That is why I just read this title for today. That is why when Einstein said, let's go to 4D space, the people say, oh, what does it mean? Okay. Because this is quite, but mathematically speaking, it's pretty natural. Einstein's teacher, Minkowski, is Einstein's teacher, and he actually, after Einstein put his student proposed his relativity in less than 2 years, Minkowski proposed that the Einstein theory can be well described by in the 4D space. So this is Einstein's 4D space. So this is just another example. This Einstein. This is relativity, Einstein's relativity. They are related in the 4D, okay, in the 4D. And this 4D is called space-time. Do you agree? We'll talk about that space-time.
Yes.
Space-time is integral part. Okay. So to cut the story short, Minkowski said, well, everything can be simply described as a vector in the 4D. For example, the position of the point in this space. I don't want to use the same notation. Can we just use R? I guess nar. The notation, the space, you see, in general, we will describe the space. By the way, if we just describe the position of Earth, how many variables shall we use? If this is coordinate, see this is coordinate. So this is let's do it better. Let's do it better drawing. So this is, can you see? Can we call this X is Z? This X is Y and is X. Okay.
Yeah. So 3 dimensions.
Roughly, yeah, there's 3 dimensions. Okay, there's 3 dimensions. Now the question is, how many variables must we use in order to describe the position of Earth at any time?
I think 2.
Yes, exactly. Just X and Y. Do you agree?
Yeah.
Because no matter where are these, so this is just in the plane. Can you see? Exactly on this plane. Can you see?
Yes.
So therefore, if you draw the vector here in this case, you see that? And the vector also span. Can you, that's verbs. This span, can you see?
Yes.
This span.
Yes.
And of course, this vector is used to describe the of the Earth's position. Okay. And however, you can also imagine there's any vector in this space. In the mathematically speaking, mathematical space. Can we draw another different color? This is another vector. Can you see? This vector could be used could be described, for example, describe the spaceship from Earth to the Mars. Can you see? They described how to go to the Mars, and then they go orbit the Mars, and then return to the Earth. Can you see?
Yes.
Can you see the moving arrow? Can you see the moving arrow?
Yeah.
Okay, it's like moving picture. Okay.
Yes.
So, however, this guy cannot go up. Can you see? They are constrained. Can you see the words constrained in the 2D? Can you see?
Yes.
So this vector is constrained to the 2D, right? However, in the real space, our space is actually 3D. Okay, but for this particular motion, we call this 2D motion, 2-dimensional motion, dimension for D. So this is a 2D motion.
Yep.
Okay, it's very important because sometimes physicists are interested to study lower dimension phenomena. For example, they just confine the molecule in just a very thin film. Okay, so that the molecule have no chance to bump up and down, but just move around. So these will be very close to the scenario in the case of the Earth in the solar system. I hope this will give you some idea what is dimension. And let's just return to the 4D. Yes. And instead of say, when we describe the object in the 3D, what can we do? Can we just use another formula? Can we use this white color? Say, if we do describe the object in the 3D, okay, that could be beyond this, because this can be beyond this plane. So how many independent variables do we need?
In that case, we need 3.
Yeah. What are they?
X, Y, Z.
Yes, that's right.
X, Y, Z.
Yes, Y, Z. Okay, that's right. Okay, that is a space we have been used since Isaac Newton. Okay, and nobody challenging this. Say, well, the motion could be, at most in the real physical world. So in the real physical world, there's a real space. There's a real physical space. Real physical space. So when you study mathematics, some ideas, is entangled or connected with our common sense. Okay, but sometimes we have to go beyond that. So space in this case, in the physical world, we use this three variable to describe the position. So this is called a position vector, just to describe the position of any point. It's called the position vector. Can you see we use vector now? Freely we use vector. Of course, you can think, well, perhaps next time we need to describe the matrix, right? Yes, you can.
Right.
You can use a matrix to predict the motion of the Earth, step by step. Yeah, can do. But return to Einstein's 4D. Why 4D? Because Einstein want to put the space and the time together. And at that time, at the beginning, he has no clear ideas. He knows what he want, but his mathematics not as good as his teachers. And actually, he's very bad at mathematics at a certain stage. Okay, but eventually, his teachers say, well, and they got say, like, why put the X, Y here, X, Y, Z here? In addition, and he said we can just multiply another sign, ICT. Negative ICT here, that is called the fourth dimension. It's fourth variable. Can you see? What is I? Did we talk about I before?
Yeah, imaginary number.
Yeah. That is Y. What is C?
Yeah.
Can you guess?
Light.
Yeah, speed of light. Speed of light. Yes. That because too many zero, we have to use an exponent. They got 8 0, not 5. Not 5, 8. Meters per second. So the speed light speed, speed of light, photon. Okay, this is elegant. So everything can be described by the Minkowski's 4D space. But Einstein didn't appreciate much. His guy is that he said once you get fame, and he got kind of look down everybody. Anyway, but of course he got capital. He had reason to do that. But anyway, this just takes this example that we can use space. Can we turn to the space? Space can have different dimension. Okay, therefore their span will be different. Can you see? Or their freedom, their degree of freedom is different. Can you see?
Yes.
I hope this has answered your question, right?
It has, yes. Yeah. It has.
Of course,
it's easier with a physical interpretation.
That's right. When you're talking about the last time we talked about the population, so we're talking about population. We do use a vector. Do you mean? So that is called a vector for population or population vector, and is also in the space. I use this example? It's called the population, female population vector. So what do we do? So you have the total. For example, you have total population, and you got information including the total population, the total population. It's just how to use a space and vector to describe the object or phenomena we're interested in. The total population, you can use a PT, the total, the capital T. And the total population will equal to the summation of 8 different age group, okay? And because can P1 plus P2 plus P3 until Pn, okay? Can you write a sigma? Can you use a sigma notation for this pattern?
Yes.
Yeah.
Absolutely. Where's my pen? So we need equals sum of. sum of pi.
Yep.
Where I equals 1 to the n.
Yep, good. Okay, this process called the formulation. So we have to do formulation, okay? But at this stage, it is this different age group, okay? It's age group. This age group, say age group 1, age group. You have divided into the age group 1, okay? For example, baby from 0 to say for 20, for example, or for 10 or 5 years interval, okay? But this notation is a little bit is not very handy, so that's why we have to invent the vector. Can you help me to solve this problem? If we do want to write it more like
yes.
a vector, yeah, how can we make a vector to describe this in space, in n dimensional space? All right.
Yes, I guess we would just have it looks something like.
Okay.
Like
you write as a form, matrix form already. Okay.
Oh, Pn.
Yeah. That's right. That's good. That's good. So basically, can we call this is our vector? So these vectors. So this vector. Okay. So basically, we just move this copy here based on the total population. So the population vector. Can you say population vector? Of course, it is a function of time. Do you agree? It is a function of year time. So therefore, that is how we denote this. Can you just rewrite that a little bit? So there's a population. It is vector. Okay, it's a vector, and it's a function of time. Every year, this vector were different. So then we got the P1, year 1, year t. And you see, they're all the function of time. P2, yes. T, until Pn. Okay. So these will represent a vector in n-dimension space, n-dimension space, n-d-dimension space, all right?
Yep.
Or you can say this is come from, so this is, or you can say that, you can say slightly you can use a vector. So this is a vector that is in a 3D, R3. Can you say, oh, not 3, N. Can you see N? So different notation, same meaning.
Yes, I see.
And alternatively, we can actually write it as a matrix, right? If you have the, if you have the base, how do we write this? We write this as a, how to say the base. So this is total population. This is total population. This is total, right? Total. Now, if we do want to write it in as a component form, can we do that?
In a matrix?
Yeah. Can we rewrite this as component? Can we just rewrite this as a? So this is a scanner form. Can you see? This is scanner form. Scanner. Okay, scanner form, right? Can we transform this into the vector form?
Yes. Well, I mean that isn't just that. A different vector form.
Oh, you can we just draw, because n, if n is more than 3, we can hardly draw it. Okay, so that's a problem. But we can also pick up one of two dimension. Although this is this is n dimension. Okay, to see what can we do. So in the n dimension, can we call this is just U1, U1 and U2. Of course, this is a base, okay? U are base, okay? You remember we're talking base. So U is a set of base. So this is the base, the set of base. So that is, how do we denote that set? So the set of base were equal to, I will use this sign. So this is the unit vector into I here. That is that notation for the base.
Yes.
Okay. So this vector, just like a directional vector, like ijk, which is conform. Oh, by the way, if you go to just ordinary 3D, this unit vector became just ijk. That's a 3D. I hope you can remember that.
Yes, yes.
Yeah, that's if you just talking about x, y, z in the 3D real space, and then that 3 base will be just 3 perpendicular orthogonal, right? That would be a 3 unit vector. That's called I, right? It's different color. I, J, and K. You see?
Yes.
The length is the unit, but the direction matters. The direction is tell us that which direction in space. So that is called IJK. I just write down here because sometimes we have returned to this simplest case. Okay, IJK. So that's 3D. That is a 3D space. 3D space. Or in mathematics, we just denote as R3. Okay. In this case, we just pick out, see this in these times, n is I equal from 1, 2 until n. Okay, we just assume n is larger than 3 in this case. Okay. So what we can say is that although we cannot in this case, perhaps we have to make this unit vector as well. Perhaps just withdraw that. This is put a unit vector because when we choose a set of base, and that length must be unit. Okay. So this is one of them. There's another one. Yeah, should you draw that way. So this is a we have to emphasize the unit, the base, rather than the length. Okay. So can we just redraw that a little bit? So this importance in this direction, but actually if you want to label these two particular base, can we call it U1, and U2? Okay. So this is just the direction, and this is origin. Okay. Now think about it. Think about it. What would be the components of this vector, of this particular the total vector, population vector?
It would be, I suppose it's the aggregate of all the individual subcomponents. So
yeah, that is it. This is called projection onto the space. Can you see? Can you use the green one? So this is called projection. So this one, do you remember what projection when we talk of a vector?
Yes.
Yeah, that's good.
Yes.
So that is called projection. This just represents projection. So how do we describe the projection? We use the dot product, right?
Yes.
We use a dot product. But by the way, I just read down here, this projection. Projection vector is also the vector of population. Can you see? So this population vector is in the high dimensional space, but in the plane we can only see draw their projection onto that particular plane. Make sense?
I see. Yes, okay. Yes.
So this is the total population, which is also the function of time. So not only the direction, but also the length is also changed.
I see. Okay, that's a big click
so
for me.
I'm trying. We just trying to make some connection of what we discussed last week, because I say I'm going to we can go to some numbers after these ideas. Okay, now tell me, what would be the components of this project vector onto the 2 unit directions?
The components would be the...
Can we just draw the right angle triangle here, graphically?
Yeah.
So this is one right angle triangle. There's another one. Can you see? So in this triangle, of course, you can argue this is theta here. Can we call this theta 1 or theta? Just call it theta, right? Yep. It's theta 1 or it's theta 2. Theta 2. So in this way, we can immediately obtain the vector which will correspond to the population group 1. Can you put P1 here?
Mm-hmm.
This would be the P1. So this can we draw not vector here? Can we use different color? Or yes, can we use different color here? So basically in this case, can you see? Can you see the yellow colored one?
Mm-hmm.
That will be a projection of the project vector onto the U1 direction.
Right.
Does it make sense?
I suppose my question is, what are the units of U1 and U2? Are they both?
Oh, unit vector is only give you the direction. The length of unit is always 1. Ideally, when you choose the base, for this for particular representation, you see space is just empty, all right? And in order to describe the position, we have to artificially introduce the proper position, okay? The best way is to use the orthogonal unit vectors. Do you remember?
Mm-hmm.
So in other words, yeah, go on.
I was going to say, right, the unit vectors are purely introduced by necessity. They don't have to necessarily be in measured in people or anything like that.
Oh no,
it's just
no,
they just set the space.
No. They provide the where you can study their components. And also this projection will depend on the choice of the base. So this is just one of them. So given one set, a set of base. This unit vector, this is a set of this one. You see the vector in space, just the arrow, okay? In other words, when we write in the vectors, we can only focus on this part, okay? That's it. That's enough. And this vector can be manipulated by matrix or transformed by matrix. Can we just return to the idea here? So basically we say that if we want to address the issue in relation to listening matrix, that would be the case. Can you see this is can you call the T1? That's total population, can be generated by multiply a listening matrix with this initial, can you see T0 and T0?
Yes.
This is matrix form. Sorry, this is a vector form. Can you see? In this vector form, we don't have to specify the components or age group. Do you understand?
Yes, I suppose I got a little bit confused because you mentioned that this projection vector here is very, very high dimensional in the sense that this has many, many dimensions. We've chosen 2, and my question was, because we're seeing the projection of, say, P1, does that mean that the 2 that we've chosen are this one and this one?
Ultimately, you will get this space here because it's more than 3 dimensions. It's harder to draw. But before we go further, can we just write it down here? Probably you know what I mean. So in this case, P1, can we call this projection? I forget how to denote the projection onto the space. So this is a vector. First, we have to, I draw another diagram. Can we just accept, can we call this projection vector P? It's a small p. It's a small p. Just differentiate as from capital P. Okay, capital P. So that one should be equal to P multiply cosine theta 1. That's my point.
I see.
So how, and these will be represent the population of group 1.
Yes.
Okay. So that one will be the population age group in age group 1. Population in age group 1.
Yes.
Do you agree?
Yes. Yes, I do. And is the is the main variable, like, because is theta the main independent variable here, which will, like, if you wanted to do theta 2 would be population 2,
Yeah.
theta 3, population 3, etc.
Well, they just trying to do a 3D to help you. Okay, they just this time do a 3D space. This is important so to understand. So if this is space, if this is 3D, and we have obliged to draw the vector. So this is three-dimensional space, and probably that's easier for you to understand. This is z-axis, okay, and this is x-axis, this is y-axis, and this is x-axis. Okay, that's how we draw the three-dimensional space. Now, in this case, can it happen to be that in this case, and these three vectors are the these are three vectors. Can you call these happen to be u1 and is u2, right?
Yep.
u1, u2. But of course, this in this case, because we just simplify this question. Can we just simplify into 3H group? Okay. 3H group. Then that's one. So therefore, any vector, any population vector in this three-dimensional space, can we see it here? This green arrow represents the population group. You have three population group. Can we just call this as so this to simplify, just consider just 3 group instead of n group. Okay. Consider 3H group.
Yes. It already makes more sense looking at it like this.
Yep. 3H group.
Yes.
Yeah. We will probably confined to 3H group and to discuss this issue. Okay. I don't want to go to 3D. So this is still represent U1, U2. Can you see? Two of them. Of course, U4 will be here. U3 will be here. Do you agree? In this case, U3 will be here. Just made finish. This is U3. You see? That's a more complete description of this space. You see? So the U3. 3H group, then you can imagine that the P will be in the span of this total vector will be in the span of 3. Do you agree?
Yes.
In other words, that 3 numbers will be defined any vectors, right? So in this case, the population vector can be dependent. So can we call this P1, 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 P2, and P3.
Yes.
So that is a population. This arrow represents the vector of total population. Now in this case,
that makes total sense.
Now in order to make the projection, what can we do? We just draw this. Can we draw a projection of this 3D vector onto the XYZ position? Can you see? So this projection, can you see this projection? If you can follow me, so if I draw the, can we put an angle here? Can we use a phi? Just different angle, different letters. So this projection will be equal to PT. So projection vector will equal to PT total P total multiply cosine phi. Do you agree?
Yes.
That is a projection. So this is a projection. So this is the projection of the vector PT onto XY plane. That's UV to the 2D onto a 2D plane, okay, or 2D space. In this case, it's plane, right? Described by U1 and U2. So U1 and U2. I try to use less abstract notation here. I just wanted to know, in order to find the projection, then we have to do this twice. Now this is a 3D diagram now. So can you say this must be the right angle? You see?
Yep.
So these, can we call this angle theta 1? This angle is theta 1. Therefore, we see that the population vector, the projection P1, so that will represent P1. So the finally, this vector will represent, these components will represent the population of the first age group.
I see.
Okay, so population group, yeah, you make sense. If I just write a mathematical problem, then have to write this. You have to, first of all, we have pick up the projection. Okay, that is PT cosine phi. Then have projected again onto the onto U1 direction. That's cosine theta 1. Okay, doesn't matter. This is just a number. These just represent the population in the group 1. So these will be the population, the numbers.
I see.
Population of age group 1, of age group. Okay.
Is it fair to say that if you want to find the subcomponents, that's probably not the right term, but
subcomponents,
you want it, subcomponents of any vector, it is there will be projection involved?
Yes, the projection means the projection must be involved in this case, that in order to calculate that particular components. Of course, when we write that, we have assumptions here. Nobody tell you, because they say if you rewrite the total population, I mean the vectors, if you rewrite this population as a column vector, can we call the P1, group 1, P1T, and P2T, and until P, in this case, can we just simplify? We don't want to go to all the time, the general case. Can we just consider this particular example? We have just a 3 age group, okay? We can do that. We can do that. We can do, I can use example. In this case, we got a 3 age group, P1, P2, and a P3, can you see?
Yep.
They're all the function of time, okay? It varies from year to years, even from day to day, if you want to. But of course, the idea to use metrics is we are not dealing with continuous variable.
Sure.
We are dealing with discrete variable, okay? So this is these examples. So that's how you describe that. Can you see that? That is how PT is visualized in the space. In this case, 3D space. So this case. So this is how we did visualize this P1. Can you see? In this column, can you see?
Yes.
That is how we visually, graphically describe that when we use a column matrix to describe the vector, which imply we must choose a specific basis.
Yes.
And in this case, the basis is just the U1, U2, U3. Does it make sense?
Yep, that does. Sure.
Okay. A question? I think the computer will switch off. Doesn't matter. In 5 minutes or so. Yeah. Any question?
Okay.
So what do you say? Shall we continue to talk about the population issues, or?
Yes, definitely. I really enjoyed the Leslie matrix stuff.
Yeah, this matrix is one of the very good example that where you can predict the future based on the past. Okay, that is idea. That's the idea, and it seems that the more the data, the bigger the database, and the more reliable. Okay, but again, I mean, this can be problematic because you don't know. Nobody can predict the future. However, to some degree, you probably can give some short range, okay, short range prediction, and short-term prediction, okay, and at least to unless something dramatically change, okay. You see, yeah, go on.